record all students are in the class. Okay, so recap. We are going to go through all this term many times for the next 30 minutes. The first one, we're going to mention equation of state again, which is rho equal to P divided by RT, and this one apply to ideal gas. So every time we mention equation of state, maybe I ask one of you to answer, give me what is equation of state. So you should able to give me this answer, rho equal to P divided by RT. Right, rho density, P pressure divided by constant value of gas, and then T is the temperature in Kelvin. Okay, so I think at least by your side you should already have table 1.8, this one. So later on I will ask you a question about this table. Okay, and then we have covered what is CV, which is specific heat or for the constant volume, and also another one is the specific heat at a constant pressure, which is this one. Okay, we already have this one, and then H is the enthalpy. Enthalpy is our H hat, consists of internal energy and pressure energy. So this is also important. We will look at this many times today. And then we have another called K, constant value, specific heat ratio, which is you can find in the table 1.8. And another one is entropy, where we stopped for the at our last class. So entropy given you by S. Given you by this equation. Right, so last class, we stopped at this slide, right? So you can define your entropy with these two equations. The differences is one we use CV, another one is use CP. Both give you answer, and how we apply this one is depend on the question, depends on the parameter that we have inside the question. Okay, both give you the same answer. Need to be careful is the positive and negative sign here, and then the parameter that we use for each of these formula. Okay, so maybe in your handout, you need to remind yourself that these two equation is very important. This one is for the this one is under your tutorial question number 7. So these two equation is very important when we want to come across the entropy. Okay. All right. Now the next thing that we need to learn today is what is adiabatic. Adiabatic, this word you will see a lot of time in exam. Adiabatic means there is no heat transfer. There is no heat transfer. So in the equation just now, your entropy equal to 0 means your change of entropy equal to 0. It means that there's no heat transfer inside there. It means all the energy inside in the system is the same. All right. So when you have the question mentioned about the question analyze or assume the system is adiabatic, then straight away you write this equation. Delta S equal to 0, and these two you write either one also correct. So you write either this one or this one equal to 0 also correct. All right, and then another one is called isentropic flow. So isentropic flow, the raw word or the origin word, you see the isentropic word here. Isentropic means it was very near to entropy, which is our S. So isens means same. Isens or iso means is same. So you have isentropic means you have a constant entropy flow inside the system, which means equation 1 will equal to equation 2. Both equal to 0. Now, when you write this equation, it means that you have an isentropic flow. Isentropic and adiabatic flow. So there are two. So this equation means your system is having isentropic and adiabatic flow. Yeah. All right. Okay. Then the next one is this one. This and this is also important formula for this chapter. So this top equation is for isentropic flow. And then this one is when we have an ideal gas scenario. Is this one you need to write somewhere, or this is we call it, this is the fundamental of chapter 6, where every time you have a ratio, temperature ratio, density ratio, pressure ratio, at 2 point, 0.2, 0.1, 0.2, 0.1, 0.2, 0.1. So let's say if in a question you only have density and pressure, you can convert from this form into temperature form. Okay, I repeat. So for chapter 6, we will look at temperature, density, and pressure. And when you have an ideal gas scenario and not isentropic, but ideal gas scenario, in the question, if you only have, for example, you only have temperature ratio and pressure ratio, or you only have a temperature ratio, you can convert the temperature ratio with a K ratio. You can convert this one into either density or pressure by using this equation. So you can see from here that temperature ratio and pressure ratio is different by K divided by K minus 1 exponential value. So if you want to compare temperature and density, for example, this is temperature ratio and density ratio. You know that this is K divided by K minus 1, and this one is K. So you can simplify the equation by dividing the equation both sides. Then you will have, meaning you take out the K, you divide both sides with a K, means you can relate temperature with 1 over K minus 1 equal to density 2 density 1, like this. Okay, but anyway, it's good that you memorize this equation, because this one will help you to solve the problem more easily by looking at this, because from here you know that what is missing or what you're going to focus on. Okay, so I really highlight for you. So this is very important. And also when you another one is that it's a ratio between pressure and density with the power of K. If you have P divided by rho power K, it will equal to a constant value. Okay, we will look at one example, how to use these two equation later on. Okay, any question for this slide? Any question want to ask me? No, so I think all of you able to absorb all this information. Okay, we look at one example. Okay, so this example is a very simple scenario. When we have a pipe, and then this pipe, we have a diameter of 0.1. This is under question 11 in your handout. All right. So, and the question go like this. Airflow is, you have a steady airflow, air, the medium is air. Between two sections, section 1 and section 2, It's a long straight portion with so and so diameter, 0.1 meter diameter pipe, and then you have a uniformly distributed temperature and pressure at each section, meaning you're given temperature 1, pressure 1, temperature 2, pressure 2. All right. Now we're going to find 4 things here. So the first thing is the change in internal energy. Okay, internal energy. Okay, I'm going to ask question already. So internal energy. Praka, so what is the symbol that we use for internal energy?
For internal energy.
Yeah, what is the symbol or what is the alphabet that we use for internal energy? Okay, I'll give you some choice. Option 1, we have H hat, we have S hat, we have U hat, and we have yeah. So which one? Which one is
U.
internal energy? Okay, so internal energy is U. So the first one,
Yeah.
we're going to find the changes of internal energy. So you have U2 minus U1. So this is the strategy where you're looking at. So there is a formula for about this one. Okay, if you can remember. Okay, then the second one, enthalpy. So I'm going to ask Joshua. Are you there, Joshua?
Yes, sir. H.
Okay. Enthalpy is H, correct. Okay, good, Joshua. And then another one. Brian, are you there, Brian? Is your mic working today? Brian?
Yeah.
Yeah, so which one represent what symbol or what alphabet we use for entropy? What symbol?
For H. What am I? S.
S, okay, correct.
Entropy or
Entropy. I asked about entropy.
or S.
Okay, S, so the last one is S2 minus S1. So we already seen there's a formula for S2 minus S1. The second one is enthalpy. So we're going to find H2 minus H1. The third one is change in density. So change of density means rho 2 minus rho 1. So this one I think don't need to explain already. Okay, so before a soft question, most of the time the question already give you some hints about what we're going to ask you. Of course, this one is more direct, more direct. In final exam, there will be some guided question in front. So we change the scenario. So what something happened there, then calculate this and this. Okay, so this one going to happen in the final exam. Okay. All right, so what are the strategy we solve? Actually, not very difficult. All right, as long as you identify the correct equation, you're able to find. So the first one, the change in internal energy, we're going to find the U, the change of U2 minus U1 with the hat. So go and find the equation. So we have this equation. So you take the change of internal energy equals CV and the change of temperature, T2 minus T1. So this equation you already know already. So pull out this equation based on what the question asks you. Okay, and then recall what is the CV definition. CV equal to R divided by K minus 1. It's just like Lego, you plug in. Okay, then how do you find R and K? R and K you find in a table 1.8. So this table is given to you in your hands up or inside your exam paper. So this table can be found in question 1, in your hands up question 1. Under there's a table. So all these things already given in a table, and we are having an air. So we go and look for air, and then you just extract information from this table. Okay, which is this row. Okay, right. So I'm going to ask question again, just to test whether you understand this table or not. Vina, are you there, Vina?
Yes, sir.
Okay, Vina, from this slide, I'm going to share my screen now. From
Okay,
this slide, so what is the K value for air at 15 degrees C? What is the K value? What is the specific?
15 plus 273, sir.
What is the specific heat ratio K in this table for air?
You mean the temperature, sir?
No, I'm asking you. Give me the value of specific heat ratio K for air. What is the K value?
1.4.
Yeah, correct. So 1.4. So good. Good job. All right. Now, this table, you need to be careful on the unit. You need to be careful on the unit. So again, the temperature here is yeah.
For the air, and water, we use a standard number, right?
No, for chapter 6, you need to be careful on the temperature. There's no standard temperature here anymore. Okay, so of course, every time when you see the question, the question do not mention any temperature, you need to refer to table 1.8. Okay, normally the question will mention the temperature like what you've seen in test 1. So in this case, we use temperature 15 degrees C. Okay, 15 degrees C. Yeah. Okay. One thing I need to change from the question is that in this case, the temperature unit is wrong. Are you able to spot that there's a typo error inside this question? If you refer to table 1.8, what is the temperature that we should use for chapter 6? Let me ask question. Okay. Su Jinghao, are you there?
Yes.
Yeah. So what is the temperature unit that we should use for chapter 6? What is the are we using Celsius or are we use other unit?
Not Celsius. I think it's the K.
Yes, correct. So make correction in your hands out. So the temperature is not R, it should be K. So again, this PowerPoint slide, there is a typo error where the temperature is not R, but it should be K. So yeah, this is some awareness that you should have. Okay, good. Then you have all this value. We continue with the question solving. You substitute all the value, all right? And then the R value you should have 2.869. Yes, correct. Yeah, any question?
So what if the temperature was given in Rankine and we have to change it to Kelvin?
Yeah. So no, in this case, you don't need to change. Yeah, you don't need to change anything. You just refer to table. For example, in this case, the temperature for in this case we only look at T1 and T2, right? So in this case, we will use the value for air. For example, K is 1.4. So we will use this value for in this calculation. You don't need to convert anything. You just plug in the number that you see inside table 1.8. You understand not? Yeah. So because we assume our air behave as ideal gas, so we straight away we go to table 1.8 to look at the we can say that it's a standard value for that particular medium. Okay, because CV value is you can say is fixed, already fixed. So CV value given by R divided by K minus 1. So R you can extract from this table. R is 2.869. E plus 2 means 10 power 2. The unit is joule over kilogram dot Kelvin. Okay. K already given, which is 1.4. You substitute this one, you find your CV. Okay, you can find your CV. Okay, you substitute this one in, you get this CV, 717.25. The unit is joule over kilogram Kelvin. Then you have the temperature here, right? You have 540 and 453 Kelvin. Again, this one is Kelvin, not R. Okay, so you substitute inside there. You take out the Kelvin inside the CV there. So at the end, your change of internal energy will be negative 62.4 kilojoule over kilogram. Okay, this kilojoule, you need to be careful when you answer question, is that I always recommend you do your calculation in a joule over kilogram per Kelvin. After that, you get a very let's say you get a 5 full number. You convert this 5 full number into either kilo, mega, or something. Okay, don't straight away jump into kilojoule over kilogram. So these are all the calculation mistake that most of the time I see in exam. Okay. All right. Negative means the energy is lost. Negative means energy is lost. Okay, so any question for the internal energy for when we want to find a change in internal energy? This one quite straightforward. Okay, so this section A is just that to test you whether you know what is the equation for internal energy. So we have covered this one in our previous lecture already. And then how to find all this value is very easy if you know which table to refer to. All right. The second one, change of enthalpy, which is our H, given us by this equation with the Cp times the change of temperature. Then recall again what is the definition for your Cp. Again, Cp equal to Rk divided by K minus 1. Okay, or you can find either one. Right, you can find either one. You can use K equal to Cp divided by Cv because just now you find your Cv already. But again, the value of K you can find from the table 1.8. So just in case the K is not given, but you calculate the Cp or Cv, you can still find the K. Right? So you can find your Cp from Rk divided by K minus 1. You'll find around 1004.15 joule over kilogram Kelvin. Substitute all the value you know. You have the T1 and T2 value here. Again, the temperature here is Kelvin, not Rankine. Kelvin, okay. You will have your change of enthalpy is negative again. Means there's a loss of enthalpy. All right. So negative at the 7 point something kilojoule over kilogram. So
Sir,
this, yes.
isn't usually CP and CV constant?
Which one?
CP and CV.
Uh-huh.
I mean, usually we cannot find it from the table.
Usually you can find the table. I
We
will
need
show you
Saturday?
more and more table today. Yeah.
Okay.
Yeah, because the table 1.8 is very limited. But today I'm going to show you a lots of table.
This one for air, correct?
Yes, this one for air, correct.
All right, thank you.
Okay. Right, so the change of enthalpy we clear already. So just now we find change of internal energy, internal enthalpy straight away, just application of what we learned from the formula. We plug in, then we find the answer. The next one is a little bit challenging, but can do. So we need to find the change of density in section 1 and 2. This keyword is actually testing your understanding in the equation of state. Because equation of state tell us section 1 will be if you use the equation of states, you can equal section 1 and section 2, means the state in section 1 equal to state in section 2. What does it mean? It means if you want to find the change of density, means you take row 2 minus row 1, you write in the equation of state, means equation of state number 1, you have P divided by RT, means all the parameter here referring to section 1, all the parameter here refer to section 2. So we know that the change of density, we always take the second one minus the first one, means output minus input. 2 minus 1. So we rewrite the equation of state so inside this here.
Can we use for this question isentropic flow, that the rho 2 over rho 1 equal to temperature?
You can, but yeah, this one you can use that one, but it will be more complicated lah. So in this case, we straight away use equation of states for this straightforward question. Yeah. So for the equation that you mentioned just now, we most of the time we'll use it for nozzle. We use it for converging and diverging case. Okay. Later on, we will look into that particular things. Okay. So for this question, we will look at a change of density. We use the equation of states because all these parameters are given. So why you want to use a more complex equation, right? So of course, there are many equations that you can use. So this is the most simplest way. So we have the temperature with the pressure. So R we can find, right? R is inside table 1.8, right? So you substitute all the value, you can find the change in density. Of course, I will let you go and calculate it. But important is you know the strategy in solving the question. That is more matter to me. Okay, should be no problem in for section C. This is the application of equation of state. Okay, let me ask one very simple question. Yes.
You mean the density of which part and which part?
This one, section 1 and section 2. So we're going to find the change of density between section 2 and section 1.
You mean the one that's given up, correct? 0.127?
Which one? 0.127.
B2 is 0.127.
Oh, you mean P, is it?
Yeah.
Yeah, correct. The density is based on the equation of states. Mean P2 is this one, no? P2 is this one. P1 is this one, no? And
but did
be
we
careful.
find the density before?
No, the density is because we find the density is because the question asks us to find.
Okay.
Yeah. I mean, this question was set up just to tell you that you can use a equation of state to solve.
So they just want the row 2 minus row 1. They don't want row 2 and row 1.
Yeah, you in this case, yeah. Row 1 minus row 2 normally we don't use. Normally we will use the end minus the beginning. We normally we do that. We don't use the 1 minus 2. Okay.
All right, thank you.
Okay, right. Okay, so should be fine for C. Forward. The next one is entropy. So entropy is our S. So know that we have two equations for delta S. We have CV and CP. Just now we have two equations for this one. So I'm going to show you the first one. Okay, the first one we are using CV. CV we already find just now. R from table. T2 we can find already given. Again, this one is in Kelvin. This one is in Kelvin. So all these you can find in table 1.8. And again, row 2, row 1, we don't have. Just now, we only find row 2 minus row 1. We only find the difference, but we do not know the individual value for this one. How do we find? There's a way. There's a mathematical way. We call out the equation of state again. Call out the equation of state. Convert that this term into the parameter that we have. Right? We can convert row 1 equal to row 2. We can put in this term, mean that row 1 equal to P1 divided by RT1. Row 2 equal to P2 RT2. You divide these two. You divide these two, you will get mathematic form P1 divided by T1 times T2 minus P2. Okay, these two become this one. It's a mathematic form from this equation. Row 1 divided by row 2 by using equation of state. We can write in P1 divided by T1 and T2 divided by P2. So why we need to do this conversion? Because all these parameter was given in the question. Okay. So mathematically, you can find all this ratio by using the number given. Then you continue with the calculation, right? The next one is just show you the changes from the formula with row 1, row 2 into the P and T term. You substitute all the value, you will get the answer. Okay, you get the answer in the kilojoule over kilogram. Sometimes you only get joule over kilogram. It depends on the value that you calculate. Any question that we use S2 minus S1 equal to CV something? This equation, any question?
Sir.
Yeah.
I don't understand the second part.
Which one? This one. This one, is it?
Yeah. I mean, before that.
Yeah.
The derivation of it, yeah.
You mean from P1 divided by P2, row 1 divided by row 2 equal to this one? You don't understand, is it? Is this one the part you lost?
Yes, sir. I don't know where it came from.
Okay, so again, I explain. So we're going to use equation of state. So what is row 1? Row 1, we can write in equation of state P1 RT1. So we can write in this form, correct? Then
yes,
we can write row 2 also. Row 2 divided by RT1, correct?
Yes.
So we have this ratio. So we take so we have R, we don't need to change. R always same. R is the constant value. We don't need to put, you can put 1 and 2, but actually R1 and R2 is the same, so you don't need to change the equation. Okay, so I'm going to do the mathematics for you. P1 divided by RT1, this is the first one. Divide by P1 RT2. Oh, sorry, this is 2. Okay. So mathematics, how you convert this one into multiplication? P1 R T1 times, you reverse these two, R T2 P2, and let me change the color of my monitor. No need lah, I just straight away. From here, you take out the R. At the end, you get this term. Okay, you get P1 divided by T1 times T2 divided by P2. This is mathematics. This is mathematics. From this one, convert into this term. Okay, do I explain? Do I answer your question?
I got it, sir. Thanks.
Got there? Okay, good. Now you have all these kind of question in your final. You need to do conversion one. You won't be that direct. So most of the time you need to use the equation of state to change the parameter there. Okay, again we will do a lot of tutorial for this one later on. Okay, So the rest is just substitution, then you get the number. Okay. Okay, so I think we have done with this question, with this tutorial. Anyone want to ask me question? Any parts that you lost? Okay. Anyone want to ask me question about this part, about this equation, about this question, question 11? This is quite straightforward, and this one is for straight pipe. Later on, we're going to see more complex with convergent and diverging pipe. Okay, so at this moment, we'll look at very simple, straightforward first. At least you get some idea how we apply the equation for entropy, enthalpy, how we change the rho using equation of state, and then the energy, equation of energy, by using the definition that we have. Okay, if no, you're going to move forward. Okay, so another solution just now I mentioned. First one, we use the first equation with using the CV. But of course, you can use the CP equation, which is more direct lah. So you don't need to do conversion. Straight away, you use a CP. And then the second term here is negative R ln P2 minus P1. All these parameters you have. So in the exam, the answer will be the same as the previous one lah. So in the exam, choose wisely, because the time is given is very sufficient for you to solve the question. Okay?
So,
yeah.
We are using a CP equation for the entropy. We have to change to the CV, right? At last.
Don't need. You straight away, but you have to calculate the CP lah. In this case.
Oh.
You have to calculate the CP. CP is given by this equation. K divided by this one.
Okay, yeah. No, last chapter say if we have got a CP, then we have to change to the CV.
No, if it depends on cases. For in this case, the question only asks you the change of entropy, and then you have the pressure, temperature parameter. So and then you know that equation for entropy you have two equation, right? So you can use either one to find the answer. You have these two equation. You have these two equation. You can use either one. Okay, you can use either one. Because of course you have to know the definition of CV and CP lah by using the K and R value. This one, these slides. You have to know the conversion of this one. Okay, you have to know the conversion. CP equal to RK divided by K minus 1. CV equal to R divided by K minus 1. So it gives you some flexibility to solve this kind of question. By if you ask you about entropy, then you can choose either it's CV or CP, but be careful on the term that you use. One is positive, rho, one is negative, pressure. Okay, I think I explained very clearly for this question. Okay, move forward a bit. Okay, the next one, we're going to look at question 12 in your handout. We look at Mach number. So what is Mach number? Remember this equation. So Mach number, MA equal to V divided by C. V is the local flow velocity or your upstream velocity. C is the local speed of sound C. And from this point onwards, the value of C will change. The value of C will change according to temperature and their K value. Because C, from today onwards, the equation for speed of sound, local speed of sound will be given square root of RTK. Okay. Before this, we learned about Mach number. Mach number is a ratio between velocity and speed of sound. Today, you learn one new equation for speed of sound given by square root of RTK. This equation is important. It will not given in your final exam. All right. So by memorize, you know that C equal to square root of RT for chapter 6 question. All right. You memorize like you memorize the gravitational acceleration, 9.81. Okay. So every time you saw, you need to find or you need to use the speed of sound, straight away call out this equation. C equal to square root RTK. R is from the table 1.8, which is the gas constant. T you can will be given. K you refer to table 1.8. And this is just a side note. C also can be given in the Buck modulus of elasticity, EV, Buck modulus, square root of rho over EV divided by rho. So of course, this definition I won't ask you in final exam. Okay, but this definition I just give you hints. So you need to know what is the definition of the speed of sound. Okay. Right, so if you look at the table in your hands up question 13, where you see exactly the same table as on your screen now, which is table B.4. So if you look at B.4, what parameter you have here? You have temperature in Celsius, density, specific weight, dynamic viscosity, kinematic viscosity, specific heat ratio K, and speed of sound C. So this is for air. This table 1.B4 is for air. Each medium will be different. CO2 will be different, nitrogen will be different, water will be different, and all this. But this table B.4 is for air. And all this value is interrelated. So we're going to verify very quickly the speed of sound for air at 0 degrees C, which is this one, is 331.4 meter per second. We're going to prove this value in a very simple mathematical way. Of course, in exam, I won't ask you to prove. I'm going very fast. How this value can be found, right? So what is the equation for speed of sound just now? Let me ask question. Bilal, are you there?
Yes, sir.
Okay, what is the equation for speed of sound?
The speed of sound is
square root of what?
I just thought it's RKT.
Correct. Square root of
RTK.
RTK or RKT, also correct. So yes,
RTK,
very good. Good job. All right. Yeah, so going very quickly. So we know that our K is 1.401. Yeah, our K value, we're going to prove, we're going to prove the value inside this table, which is 331.4. How we get this value? K from here is 1.401. 1.401 at 0 degrees C. So we apply this equation, square root of RTK. If we substitute all the value there, R from table 1.8, 2.869 10 power 2 joule kilogram dot Kelvin. If you put all the unit inside there, your C will arrive at joule over kilogram square root. Why do I get this unit? What is the unit for Rankine? For R, joule over kilogram dot Kelvin. T is in Kelvin. K is just a ratio, have nothing. You have nothing here. So if you take out this one, the unit you have is a square root of joule divided by kilogram. So if you put something square root power half, it means square root. So your C is in joule over kilogram square root. But we know that in unit SI, most of the time we do not use joule over kilogram. So how do we convert this one in meter per second? So this is the conversion. So this is a conversion. 1 joule over kilogram. We know that joule is Newton meter, means force. Joule is a work. Work. What is work? Work is force times distance. So we have Newton meter. And what is Newton? Newton is force. Again, call out force equation. Force equal to ma. F equal to ma. Second Newton law. So you call out the unit. So this is ma. M in kilogram. A is meter over second square. So you combine with the previous one. Meter over kilogram. Take out all the unit, the repeated or the parameter. Kilogram cancel. Meter square. See this one, continue. Bring forward, you have meter square. You put this unit inside this equation because this one is something square root, right? So you take out the 2, at the end you arrive at meter over second. So that's why this slide explains how the unit of joule divided by kilogram square root, at the end you can write in meter per second. Yeah, this is just a dimensionless or dimension analysis. Any question? Anything that you want to ask me to clarify about this slide? Any mathematic steps that you don't understand? Okay, Noah, clear. Okay, good. We look at this example and then we go for a short break. Okay, look at this example and then we go for a short break. Now this is question 14. Question 14, it gives you the application of what we going to learn. All right. So in this case, you have an aircraft. Cruising means moving in the 250 meters per second at altitude of at the altitude of 10 kilometers above seawater, sea level. You need to find a few things. You need to find ABC. The first thing is Mach number. Mach number. First thing, find Mach number. Okay, which is your MA. Stagnation pressure, maybe is new to you, is P0, which is the air do not move. And temperature relative to the airline or relative to the aircraft. And there's a table given below the question in your hands up. So this table is C.2 is for the standard air atmospheric in unit SI. What does this table tell you is that at different altitude or different height from the ground, your air will act differently. Means that the measured temperature will change, gravity will change, pressure will change, density will change, and dynamic viscosity will change. Okay, now this table C.2 only come into place when you see the keyword of altitude, means the distance from ground, then you need to use this table. Okay, I repeat. When table C.2 you need to use in either in exam or when you go to work later on, is that when you see the word altitude, you need to find in that particular location, what is the temperature? What is the gravitational force? Right? What is your G? What is the pressure at that particular point? What is the viscosity? What is the density? Okay, right? Right. Now, Mach number, we know that the definition, V divided by speed of sound, local speed of sound. We know that just now I asked one of you, what is the definition of speed of sound is RTK or RKT, right? Right. Then the second one we need to find is what happened if this aircraft change speed double the speed from 250 to 500. Right? What happened to the Mach number? What happened to the stagnation pressure? The next one is what happened if this aircraft maintained at the same speed but change altitude? Okay. Now the strategy to solve is quite direct also. So you have you're given your speed is 250. The distance is 10 kilometer. So from the table C.2, you look at the row of 10 kilometer, which is here because the altitude unit is in meter. 10 kilometer is this one. 10,000 meter, this one. So you use all the parameter you have in this table. You have Celsius, you have gravity, you have pressure, you have density, you have mu. So if you see this value on the screen, make sure you understand. When I mention pressure at 10 kilometer is 26.5 kilopascal. Do you know how to get this value or not? If you don't know, ask me. Anyone you do not understand how, when I write P 10 kilometer equal to 26.50 kilopascal, you don't know how to find the value inside table C2. Let me know.
Yeah, I didn't understand.
Okay, how do you use this table? You are given
We check the altitude
10,
at 10.
Yeah, altitude 10 kilometer, right?
Yes.
What is the value of pressure at this altitude? You see this one, right?
It's really small.
But you can, all right. I mean, on your screen you can see, right?
Yeah.
Yeah, you're using handphone or you're using computer?
Yeah, to talk, I'm using headphone.
Okay, so next time it's good that you use a desktop. So this value, I think if you zoom, you cannot zoom. You can see 2.650 E power 4. E means 10 power 4. Means this one is 2650 Pascal, Newton over meter square. Do you get the idea?
Yes, then we changed it to kilopascal.
Yes, you change it to kilopascal.
And we remove the decimals.
Yeah, so of course you can maintain like in a Pascal unit, no problem. It's all right. You maintain what you see in the table, no problem. Then the temperature also same. Temperature here is negative 49.9 in Celsius. But again, for this chapter, we need to change all the Celsius into Kelvin. So this is the place where we change the temperature, not the previous example. Okay.
Okay, sir.
Yeah. So, and then another one is that we try to solve because the question asks us at two altitude or two location. One is in 10 kilometer, one is in 1 kilometer. In the question, if you look at the, okay, I'll show you the question. The section C, it asks you something about 1 kilometer. So you do the same from this table. You go to 1 kilometer, which is 1,000 meter. Then again, extract the information from this table. Right? In this table, you see that it is 8.988 10 power 4. Means that it is 988 is 89880 Pascal. Okay, so of course you can maintain in the what you see in the table, or you can convert into kilopascal. Then the temperature also same. Temperature in this table is in Celsius, 8.50 Celsius, you convert into Kelvin. All right, because later on you need to use the R, because Mach number equal to V divided by C. C is equal to square root of RTK. So every time you need to involve with the R value, you need to change into Kelvin. Okay, the rest is just an application of the equation that we learned so far. All right, MA, which is a Mach number equal to velocity divided by local speed of sound, and local speed of sound equal to square root RTK. Okay, you substitute, you get your C value about 300 meter per second. And I already explained how you get meter per second. Just now we do the conversion just now. So you substitute all the value, you get about 0.8 Mach number. Mach number is a ratio, so you don't have unit for Mach number. It's just a ratio. So you get a 0.8 at 10 kilometer, which is about, you can find, so from Mach number, you can find the speed. This speed is given 250. So mean you substitute 250 here, 250 divided by your C, 299.6. You get 0.8 Mach number. Any question at this point? Anyone you confused, or you don't know how to, or anything that doesn't make sense to you, like you don't understand how do I find that particular value? All this we just apply what we learned. What is the definition of Mach number? What is the definition of speed of sound? And then you're given a table C.2. From the table C.2, you refer to the respective altitude, use the value. What you need to careful is that the temperature you need to change to Kelvin. Because C equal to square root RTK, the R value here you use from the table 1.8. You times the T. T is in Kelvin. K is dimensionless. So you can find the value. So if you have Mach number less than 1, just a side note. So we'll use the word subsonic. We use the word subsonic to refer the speed is below Mach number 1, less than 1. Okay. For scenario, then the next one is because we need to use we need to find the stagnation pressure. So again, there is a table. The table is called D.1, D.I. D.I. Yeah, D.I. In your hands-out is a very big, very long table. So I just extract one of the portion. Just one of the portion. In table D.1 is a very big table. It is a table for K equal to 1.4. Mach number, you have a few columns. The first column is Mach number. Second one is ratio of temperature. T divided by T0. 0 means stagnation. Means this word, stagnation pressure. Stagnation. Right? 0 means stagnation. So the first column is ratio of temperature over stagnation temperature. Second one is the pressure. So it means pressure over stagnation pressure. Then this one is the density. So it also means density over density at stagnation pressure. We will explain about this one later. Star means critical scenario. We will look into this in the later session. Okay. So since we define our Mach number is 0.83, so it's about here, is around here. right? Your Mach number is 0.83, 0.834, so it is here. So it asks you about stagnation pressure. So what you do is that you look at these two values, you do interpolation. You do interpolation at Mach number 0.834, which is here. You do interpolation using 0.834. You can use either 0.8 or 0.85 to find the value at this point. Okay, this point that I mark across here is for Mach number that in our case, which is 0.834. You need to do interpolation. There's a mathematical interpolation steps you need to do. You will get around 0.63, which is in the middle, which is in almost in the middle between 0.65 and 0.62. Okay, I'm not going to repeat the interpolation mathematics steps. If you don't know how to do, go and ask your calculus lecturer or engineering mathematics lecturer. So it's the interpolation steps. Same with the temperature also. You take the value at Mach number 0.834. You can use either 0.8 refer to 0.834 or 0.834 refer to 0.85. Find the interpolation value at this point. You'll get around 0.87 or 0.88. For this module, again, a reminder, maximum 3 decimal place, minimum 2 decimal place. Okay. Of course, in this table, you have 4 decimal place. Okay. Right. I repeat, how you get these two values is through interpolation from the table, meaning there's a value between all this, so you need to find. The actual size of table D dot I or D dot 1, you need to go and look at your handout that I sent to you in your tutorial page number 6. It's a quite long table. So you have two sections. One section, if you look at your handout, you have two sections. One is one side on the left, and then another, repeat the same table on the right hand side. The same parameter, but the Mach number is different. So on the left, from 0 up to Mach number 2. On the right, it starts from 2 to Mach number 10. And repeat the number here. I mean, you have the temperature ratio and all this. On left hand side, on right hand side, you have that one. So the complete table, you need to refer to the handout that I give you. Okay, feel comfortable with the table D.I or D1. Okay, because most probably you will need this in your final exam. Okay. Any question on the value to find stagnation pressure or stagnation temperature or stagnation density? Any question? Anyone you lost? Ask me now. Let's say, oh, how? So how to find this one? Ask me now. Make sure you understand. Okay. No question. I move forward. So again, I show you the steps. So we will use this equation. So we know that the pressure, okay, let me write in the form so that you can understand. So how do you get this one? So for example, you get P divided by P0, this one at 10 kilometer, Mach number 0.834. This is Mach number. This gives you 0.63. Okay. Now, how do you find the stagnation pressure? You just work the mathematics. We want to find stagnation pressure. So you move this mathematic. P divided by 0.63 equal to P0, which is stagnation pressure. Where we find the pressure? In the table. How we find the pressure value here? By referring to the pressure at here. Just now I showed you already how to find from table C.2. Our pressure at 10 kilometer height is 26.5 kilopascal, or the value that you see on here, 2.650 10 power 4. Then you do the mathematics, you do the calculation, you will get pressure at stagnation state will be 41.8 kilopascal. Same with, you do the same for temperature also. Okay, your temperature at stagnation stage at a height of 10 kilometer above sea level, if you do the conversion like you did for pressure just now, you will get 254.3 Kelvin. Any question want to ask me about stagnation pressure? How do you find, or stagnation temperature?
Sir, for the stagnation temperature, we use the stagnation pressure, correct?
Again, your question?
For the stagnation temperature.
No. Stagnation temperature, you use from table D1, because in table D1, it gives you the ratio. Oh, sorry, there's a typo error. This is not P, it's a T, yeah? It's a typo error. So it's a T divided by T0, because from this table is T divided by T0. There's a typo error here. So you use the T divided by T0 at Mach number 0.83. From this table, you do interpolation just now, you get 0.88. So the temperature at 10 kilometer, just now we already find from the table. Temperature at this height here, temperature, you have a negative 49.9 convert to Kelvin. You have 223.3 Kelvin. You substitute this value inside this equation. Okay, you take, because you have T over T0, you have 0.88, for example. You want to find stagnation pressure, so it's T divided by 0.88. Where to find this T is from the table just now. Then you find the stagnation temperature. Do I answer your question?
Yes, sir.
Okay. All right. Then for B, when you change the speed, when you change the speed from 250 to 500, and what you need to aware is the altitude still same, means the height still at 10 kilometer, means that the pressure, the temperature that you find in the table just now still can use. Only now what changes is the speed. The speed will change on the Mach number, because Mach number equal to V divided by C. You just substitute. Okay, RTK still same, because you do not change the altitude, you do not change the location from the sea level. It's still at 10 kilometer per 10 kilometer. So you just change your V, your Mach number you'll get at 1.7 or 1.67 at 10 kilometer at a speed of 500 over meter square. Again, just a side note, if you have Mach number more than 1, we call it supersonic speed. Just now, if your Mach number less than 1, we call it subsonic. If the Mach number equal to 1, we call it sonic, where we will look at later on. If your Mach number is more than 1, you have supersonic speed. Okay. Again, look at this table, because table D.I or D1, we look at this table because now our Mach number changed. Our Mach number is 1.7 or 1.669, which is 1.669, which is around this 2 number or this row that I highlight. Again, you need to be familiar with table D.I. It's a very big chart. Go and look into handouts, page number 6. So if you don't familiar, you will be confused when it comes to exam. Even though you look at my slide, you are confused. Okay, because there are so many numbers that you need to look at. And this one is just a very small portion I extract from that table. Okay. Yeah, so we go to the row of Mach number. You go to 1.65 and 1.7 because our Mach number is 1.669. So you find 1.669 here. Go and find for temperature ratio, pressure ratio. And from here you can find also the density ratio and area ratio. Okay, go and find the value here. Repeat the same step. You're going to find, okay, for textbook or for your reference, if you do the interpolation again, your pressure ratio at 500 meter per second, or Mach number 1.669. From this table, pressure ratio is 0.212. Okay, the interpolation steps. And then the temperature ratio will be 0.64, 0.64, which is here, 0.64 or 0.642, 0.642. You do the same calculation. You substitute your pressure at stagnation states at 500 meter per second at altitude 10 kilometer from sea level is 125 kilopascal. Okay, the same steps, mathematical steps from here to here. All right, temperature still same. T0 equal to 347.8 Kelvin. Okay, the strategy of solving still the same, right? And again, you have my slides. You can go back and look at it later on. The third one is now you change the altitude to 1 kilometer. Now we look at 1 kilometer case, right? Forget about 10 kilometer already. You set everything calculation. You look at the table. Find what is the pressure at 1 kilometer. What is the temperature at 1 kilometer from the table. Substitute in the Mach number equation, ma equal to v divided by c. Recall what is the definition of speed number equal to square root of RTK. RTK from table 1.8. Okay, you get your speed of sound at 1 kilometer above sea level equal to 336.5 meter per second. Substitute the speed at 250 divided by 336, right? Because your Mach number equal to v divided by c. You take 250 divided by 336.5, you get your Mach number. It is 0.7. Again, Mach number less than 1, we call it subsonic. Repeat the similar approach like just now. You look at the table DI and find the stagnation pressure. I give you the reference, the textbook reference answer. P0 for C will be 129.7, and the T0 for this section C will be equal to 312.8 Kelvin. Okay, this one you do your calculation and then you try to see whether you understand or not. This is just a reference answer for you to check whether your calculation is correct or not. Okay. Okay, we stop at this example. Let me stop the recording.